sir.
Yes, sir.
Okay. Let's just wait for 2-3 minutes. Let's wait for people to show up. Are you able to see my screen?
Yes, sir.
Okay. Okay, fine. Let's start. So if you remember, in the last class we were discussing different different ways in which machine learning can be applied for different classes of time series problems. So we had talked about time series classification, time series regression, time series clustering, time series forecasting, then change point detection in time series, etc. Then we had started to discuss about the time series, that is non-numeric time series analysis. So one application of non-numeric time series which we had picked up was what is known as the market basket analysis. So just to recap, what is market basket analysis? So suppose that we have a time series of purchases by different customers from an online retail site, like say Amazon or something like that. So the task is that given the previous purchases of a person along with their corresponding timestamp, can we predict what the person is going to predict next, right? And we had also discussed why this is important. This is extremely important both for offline markets, or that is to say the standard supermarkets where things are arranged in a particular order, or it is also important for online recommendation systems like Amazon, Flipkart, and all these things. Just a second. So the reason of this importance is that especially in case of online retail systems, this is important because of the recommender systems. If we know what the user is likely to look for next after having purchased certain products, so then the recommendation engine may suggest those items to the user, and the better they are able to recommend items or relevant items to the user, the more satisfied the user will be, and more higher ratings will the that service get, and more customers they will attract, and hence more profit they will make. So so that is why all the so all these engines, they take the task of product recommendation or item recommendation very seriously, and they dig into the past purchasing history of not only individual customers but also customers as a whole, to understand that given the past purchase records of various customers, what they may purchase next. Okay, so suppose that this is what the data looks like, that we have a particular user. Let us focus on one single user for now. So suppose we know that but at time t that user has purchased A. Then we can ask that is suppose B is any other item. So then we can ask that within a short time of purchasing A, is the user also likely to purchase B? Or that it can be multiple conditions also. So suppose we know that at time t1 the user has purchased A, and at time t2 the user has purchased B, where like t1 and t2 are like close to each other. Then can we say that the next is the turn of C, that is within another short duration, that is given that A and B have been purchased at short like in the recent past, can we say that next C is going to be purchased? So these are the kinds of questions which we will try to answer from the data. So this is what the purchase database may look like. So as we are this data set we are discussing yesterday also, I mean on Monday also. So you mean there are 6 users here, and there are so many, like for each day or each time point we have these records of which user purchased which item, so arranged in the times of their purchase. So the question is this at t13, what will, if user 1 does buy something, what are they likely to buy? Or if user 2 buys something at t13, what may that be? So so like some of you yourself had suggested possible answers. One suggestion was like whatever, like in the past, whatever the user has been buying most frequently, we may predict that at t13 also the user will buy that same thing once again. A more intelligent answer was that that is, if we can actually look at the sequence in which the user has been buying things, and in that case like at t equal to like given the past or the latest sequence or subsequence of the user's purchases, can we see like if some like if we can make use of past trends, and or if we can understand that the current sequence of purchasing is actually a subsequence of a frequent sequence, then we can complete the sequence accordingly. So that is to say, for example, here we have seen that a purchase of C in the past has been followed by or rather a purchase of A, B, C in the past has been followed by a purchase of D, and once again we are seeing A, B, C being purchased in that order. So like it may be it may be a good guess to predict that D is going to be purchased next. Of course, we know that our customers' purchases are not always deterministic, and of course a customer may buy things in may buy the same set of things in a different order, or they may buy some stray things or unusual things which they otherwise do not buy, and stuff like that can easily happen. But it may be like a good guess or an intelligent guess to identify these sequential behaviors and make predictions accordingly. Okay, so so then the task becomes, we have to basically look for such sequences of articles, or frequent sequences of articles which are bought one after another, and so that we can understand that okay, so this is a sequence, and given any new purchase we can try to understand that okay, a new like one of those common sequences of purchases has started, so that we may expect that the user will buy such items that will complete that sequence. Okay. So for example, in this case, like DEF seems to be a sequence which user 2 buys. So here D and E have been purchased. So it's possible that F may be bought next. On the contrary, we may also see that so far the user 2 has purchased F only once. So it's possible that DEF is not really a sequence, but it's really DE which is the sequence, and F is just a stray thing which the user, maybe the user had an unexpected or emergency need for some extra products, or somehow he or she got attracted to a particular product and bought it, but this is not likely to repeat. In that case, it's possible that the next purchase will again be D. So there are like, of course, there is no easy way to answer this question deterministically, but still people try to like identify sequence or frequent sequences, or frequent which are sometimes known as frequent item sets, which the users buy, so that we may be we may be able to forecast what the user is going to buy next. So this is called the frequent item set mining problem. This is not necessarily a time series problem. It has also been used offline. So the one way to do it is basically to do a probabilistic treatment. So we that is to say, given the past few items which an user has purchased, we try to define a probability distribution over what the next item is going to be, instead of making a single prediction that okay, the next item in this case is going to be D, or it's going to be A. In this case, instead of saying that okay, the next item is going to be F or going to be D or anything like that, let us assign probabilities to the different items which the user may buy next. So this is the way such probability distributions are constructed. So suppose B and C have already been purchased in the recent history. Now what I mean by recent history, that may, so basically that may mean we can put something like a threshold of time, say within the past 5 timestamps or past 3 timestamps, or whatever is necessary, whatever is suitable. So given that B and C have already been purchased in that time window, what is the probability that A is going to be purchased next? So basically what so this is these probabilities are basically calculated with the help of relative frequencies of purchases, which we study or which we can read of tables like this. So like basically we express in the following way. This probability will express in the following way. First, on the, that is, we will calculate what is known as the confidence of A, B and C being brought together, divided by support of the support of B and C. What is B and C? B and C is what has already been observed, and A is what is being proposed. So ABC is basically a proposed item set. B and C is a observed item set. We already know that B and C have been brought together. Now we are like considering a proposal that A, B and C are being brought together to complete the item set. Okay. So so confidence of ABC is nothing but like the basically a frequency of the number of times A, B, C were brought together, and that is to be divided by the support of the of the evidence BC, that is the number of times B and C were brought together. So as you can understand easily, that is the event that A, B, C were brought together is definitely a subset of the event that B and C were brought together. That is, when B and C were purchased, then A may or may not have been purchased, but if ABC were purchased, then definitely B and C were purchased, right? So that means what? That means this will be a smaller number than this, or at least not a greater number than this, right? So so that actually allows us to pass off this quantity as the probability, because we know that the probability value must lie between 0 and 1. Okay, so obviously this is a positive number, so it will be above 0. But as I said, because the event ABC brought together is a subset of the event BC brought together, So definitely the denominator will be will not be smaller than the numerator. So that this probability value will be less than will definitely not be more than 1. Okay. So now the question is how many past purchases should we consider? Like, is it enough to consider B and C, or shall we go deeper into the history of purchases of A? So so there are at least two ways of looking at it. Either we can put a threshold of time, that is, I may think that okay, I am going to predict what's the user's purchase at T13. So I may see what all the users have purchased in the past 5 or 6 timestamps. In that case, these are the time purchases which I will be looking at. On the other hand, I may put a threshold on the number of purchases, that okay, what were the past 3 purchases like. In that case, we'll put a threshold on this, and doubtlessly which way we put the threshold will have a bearing on our answers. Our answers will change. So there is no unique answer to these questions, but these are just some ways in which these can be solved. These kind of problems, we can try to find an answer to them. And another important thing is that, as I was saying earlier, there may be some stray purchases. That is to say, some rare items and user may purchase which they otherwise don't purchase. For example, this F, it is possible that this F was a rare purchase. On the other hand, say if we consider, say, user 5, right? So here we can see Can you hear me?
Yes, sir.
Yes. Sorry. There was a power cut at my end, so sorry for the interruption. So let's pick up quickly. So we were discussing about this this kind of data set, and there is this sequential transaction data set, and the need to build a probabilistic treatment for it to make the to predict the next purchase. So as I was saying that it like the estimates that we make may be disturbed by the stray items or the rare items that are rarely purchased. So the solution to this is to identify which items are rarely purchased, that is these stray purchases, and prune them off. Okay, so for that we have this kind of a frequent item set matching, which is called the a priori algorithm. So I am not going line by line into the details of this algorithm. So you can study it later. What I will do is I will run you through an example of this algorithm. So this a priori algorithm was not meant for this kind of a sequential or time series data set as such, but it can be easily extended to the time series analysis. So let us consider the a priori algorithm. So let us say that there are some 4 transactions have taken place. In each transaction, an user has purchased these items. Okay, these the numbers 100, 200, 300, 400. These let's call these as the transaction IDs. And in each transaction, in the first transaction, these 4 items were purchased. The second transactions 2, 3, 5 were purchased, and so on. So this is this is not as a time series data per se. So as I said earlier, a priori is not it was not originally meant for time series analysis, but we can use it also. So let us just assume that these purchase now let us forget these transaction IDs. Let us just assume that all the items were purchased by a customer in this order. That is that is 1 3 4 6 2 3 5 1 2 3 5 1 5 6. These were these time series of purchases we have, but there are also timestamps. So now based on these timestamps, we can get an idea about which item sets were purchased at roughly a contiguous piece of time. That is to say, maybe the time gap between the purchase of the 6th item and the next purchase of item 6 here and purchase of item 2 here may be quite large, so that we can consider them as as separate windows, separate purchase windows. Similarly, the gap between the purchase of this 5 and the purchase of this one, that may be a large gap, so that we may treat these as separate windows, etc. Okay. So now let us go by I will just give you an example of how this a priori algorithm runs in this case. So first of all, what we do is make a list of the individual items that were purchased along with their frequencies. Okay, so if we are doing this thing, so for any user, we will simply see that A, B, C, D, E. These are the 5 things that have been purchased, and I will note down their respective frequencies also. Similarly, for user 2 also, we can do the same thing. So once that has been done, so we get a time that is we get a frequency distribution of the different items, and then we will have a threshold. That is, from this we can identify which purchases or which items are rarely purchased. So here you can see the item number 4 has been purchased just once out of all these purchases. So that may fall below our threshold. So we may prune this out. Now again, what our threshold is depends on you. So you can set your own thresholds, and your results will vary according to that. Now after pruning out the rare item, now we see these are the remaining items. Now we see pairs of items, that is to say tuples of size 2. So out of these 6 things, out of these 5 things, so how many tuples we can form? So 1 2 is a tuple, 1 3 is a tuple, 1 5 1 6, these are tuples. Then 2 3 is a possible tuple, 2 5 2 6, these are tuples. Then 3 5 3 6 5 6, these are all the tuples. So now what we will see is that for every tuple we will see the number of times they have been counted together. Okay, so once again we will measure the frequencies of each tuple. So you may find that for example, if you are considering 1 2, you will find that it has been purchased only once here. This like here 1 and 2 are purchased together, so I note down as 1. Next 1 3 tuple, these two have been purchased once here, and that is again in the, that is in this like in this window they have been purchased again 1 3 5 like here 1 3. So I see 1 3 has been purchased together twice, that is within the same window 1 3 has been purchased twice. Similarly we can fill up this table like this. Now every tuple we basically count how many times every tuple has been purchased together within the same window. Okay. Now we find the rare ones, which are the tuples that are rarely purchased together in the same window. So we find that 1 2 has been purchased once, 2 6 has never been purchased together, 3 6 and 5 6 also have been rarely purchased together, so we just drop them together, just drop them. So these are the remaining tuples of size 2 that seem to be being purchased quite a few times together in the same window. Now once we have finished, once we have identified these tuples of size 2, now we move on to tuples of size 3. So now using these tuples, just by combining pairs of these tuples, how many 3 tuples we can get? Okay, so if we combine these two, we get a 3 tuple 1 3 5. Similarly, by combining these two, we get 1 3 6. Similarly, we may get 1 5 6. We may then combining like 1 6 and 2 3, we will get a tuple of size 4, but as of now we are considering only tuples of size 3, so we will not consider that right now. So but next we will find 1 3 and 2 3, so combining them we get 1 2 3, then 1 5 2 5, so 1 2 5 and so on, or like so this way you will get another set of these tuples of size 3, and for each one we will get counts like this. All the tuples here may not have been shown for space constraints, but you will consider them. And then for every tuple of size 3, again you will do the same analysis, how many times they have been purchased together in the same window. So 1 3 5 you may see has been purchased once in the same window. 1 3 5 has been purchased once in the same window. Then 2 3 5 also has been purchased twice. So like we get the counts of this. 1 3 6 maybe it has been purchased just once. 1 5 6 has been purchased just once, etc. So it may that is it may turn out that like some of them are below the threshold. Whichever are below the threshold, you drop them and you like focus on only the remaining ones. Next, after this we will go to 4 tuples, that is tuples of size 4, and again we will by their count. So this way what we are doing effectively is that we are identifying the frequent item sets of different sizes, and then this will enable us to make the prediction. So that so suppose we are in the current window, suppose we see BC is like we have got so far, then we may that is we may be tempted to think or find like is BC part of a frequent item set of size 3? That is like for example, is BCD a frequent item set? If so, then I may be tempted to think that B and C will be followed by a purchase of D. But on the other hand, suppose there is no item set like BCD, but BC by itself is a frequent item set. In that case, we think that okay, this will probably not be followed by any purchase in the immediate future. Maybe something else will be, or maybe a new set of purchases will start. Maybe an A will be purchased or something like that. Okay, so this kind of a priori algorithm, this basically helps us to identify some frequent sets of or sets of items that are often purchased in close to each other, and hence it enables us to make predictions about this non-numeric time series. So like earlier in the Monday's class, I had discussed time series forecasting as an important problem. So this way now so most of the time series forecasting methods which we will study will be for like numeric time series, where the values are numeric or maybe real numbers. But even for non-numeric time series like this, if you want to do a forecasting, this is one way to do it. Okay, now let us come back to numeric time series. Now, if we have a numeric time series where we have observations at every time point, so that is of course like if you look at this one, it may look like a continuous time series or like a continuous time series, but actually that's not the case. It's actually a discrete time series. That is t at t equal to 1 we have an observation, t equal to 2 we have observation, t equal to 3 we have one observation, etc. So all those observations are plotted and joined together by these lines. So although it looks continuous, it's actually a discrete time series only. The time is discretized. Discrete time series means not in terms of values but in terms of times. So the time has been discretized into as t equal to 1, t equal to 3, t equal to 4, etc. And at each of those time points I have got a value. Okay, so now so this is so the values at the different points are some real numbers like 65.4, 65.35, 60, maybe 64.179, etc., etc. They can be any real numbers. Okay, so now given a time series, a real value time series like this, one important property of such a time series is what we call as autocorrelation. Now, what is this autocorrelation is a very important function of many time series which enables us to do forecasting. It lays the basis of time series forecasting. So first of all, what is autocorrelation? So before going into what is autocorrelation, let us consider what is correlation. Okay, so correlation may be something which many of you have heard of. So can you suggest to me like what you understand by correlation between two quantities? Anyone, please? Anyone wants to suggest what
Or
you?
how much the two quantities are interrelated with each other. If we change one quantity, what's the difference? What difference does it make in the other quantity?
So what is that? That's right. So it's a measure of interrelation between the two quantities. So what is the what is the typical value of correlation coefficient between two quantities? Like what range does it take?
0 to 1 or -1 to 1.
Minus 1 to 1.
Minus 1 to 1. Okay, right. So suppose I have two random variables u and v whose correlation coefficient is 0.8. Okay, then like intuitively what does that tell you about these two variables?
But it shows that if we change one variable, it has a strong impact on the other variable as well.
Not just a strong impact, it's a similar impact. That is, if u increases, then v also increases by a comparable amount. If u decreases, then v also decreases by a comparable amount. But on the other hand, this can be negative also. Correlation can be negative also. Say the correlation, if I say the correlation between u and v is minus 0.6, that means what? That means if whenever u is increased, then v will have a decrease by a corresponding by a comparable amount. Okay, so this can be quantified in the following way. This is the definition of Pearson correlation coefficient, which the standard correlation coefficient, which many of you may already be knowing. So if whenever we have two random variables u and v, the random variables will have their own variances and then they will have their covariances. So for the lack of time, I will not go into a recap of what is variance and covariance. I hope all of you know that. If you don't know, please look up because this is an important concept. Now the square root of variance we know is called the standard deviation. So so basically the definition of Pearson correlation coefficient between any two random variables u and v is defined as the covariance between those two random variables divided by the square root of the product of variance of the two variables. That is root of variance u times variance of v. So we know that square root of variance of is called the standard deviation. So we can just write standard deviation of u times standard deviation of v. Okay. Now, suppose you have so this is true for any two random variables u and b. This is like the way we define the correlation between any two random variables. Now coming back to time series. So suppose I have observations at various time points. So I may be asked to I may be interested in answering this question. So for any time point, like are xt and xt minus 1 correlated? That is to say, whenever like consider any time point, say t equal to 29. So suppose at t equal to 29 there is a rise in x. If x increases, does it automatically mean that at t equal to 30 also there will be a rise? Or say suppose at t equal to 45 there is a drop in the value of x corresponding to t equal to 44, then can I expect that there will again be a drop at t equal to 46? Right. So so if these things happen, then we can say that xt and xt minus 1 are correlated. Or instead of focusing on at correspond or like consecutive time points, I may also be concerned with the correlation at a distance. Say t is say like consider a distance of delta, say delta equal to maybe 10 time points. So can we say that like x25 and x35 are related? That is to say, like if the time series has an increase at 25, then can we all necessarily say that there is going to be an increase at 35 also? And if so, will there be an increase at 45 also? Can we say such things? So to answer such questions, what we do is we measure what is known as the autocorrelation at different time, like for different values of this lag. So delta equal to if delta is equal to 1, then that basically means that we are considering lags of 1. That is to say, we are trying to like basically we have two versions of the same time series. One is the observations as we see it, and the other is a lagged version of the time series. That is to say, instead of x2, I will consider wherever I have x2 in the original time series, I will consider x1 in the lag time series. Whenever there is an x3 in the original time series, I will consider x2 in the lagged time series. So basically, I will get two versions of the time series. One is the original time series like this, and another is the lagged version of it, where this is shifted to the left by one step. So now what I am going to do is I am going to construct the correlation coefficient between these two time series. So here correlation coefficient is defined between two random variables. What do I mean by now a correlation coefficient between two time series? Answer is very simple. You just consider that the two time series you are considering, the original one and the lagged ones, these are actually just two random variables, and the values which you are observing are simply realizations of the random variable. So a random variable like u, that will have multiple realizations, right? So if you have a particular coin, and if you toss it 100 times, you will get head and tail values. So each of those values are basically the realizations of that random variable called the coin. So in this case also, it's like the variable x, that is a random variable, and we are and we are basically considering different realizations of that random variable at different points of time. So now we are considering two random variables, the x itself and the lagged version of x. Okay. So once I construct the correlation coefficient of that time series, I mean, once I construct that lag time series, it will have its own correlation coefficient. I measure it and I put that value, and I just note down that value for different values of lag. That is, for lag equal to 1, I will get two time series, so I will compare their correlation coefficient and note them down. For lag equal to 2, I will again get two time series, the original one and a two lagged one. So I will I'll measure that correlation and put it down, and so on. Okay. So this plot, what I am showing on the right side, is basically the for different values of lag, for different values of this delta, I am plotting the correlation coefficient. So needless to say, when delta equal to 0, what happens to the correlation when delta equal to 0? How much should the correlation be?
1.
1, because you are just comparing the original time series with the original time series itself. So at delta equal to 0, so as you can see, this is a high value, so the correlation will be 1. But for higher values of delta, say here I have shown the plottings of delta all the way up to 20, say 1 2 3 4 all the way up to 20. You can see that for higher values of delta, the correlation coefficient seems to be quite low. That is quite, its magnitude is just between -2 and 0.2. So that's a low value. So that means what? That means that there is very low autocorrelation between time series, in this time series. So if at any point the value of x increases, we cannot say that at any other point also or any other particular point, we cannot say with guarantee that it is also going to increase. Okay. So that means that this particular time series does not have very good autocorrelation. And because it does not have it, so it's very difficult to predict the next value. This concept of autocorrelation, this basically helps us in being able to predict the time series. If I can say that the time series shows some kind of autocorrelation, then we can utilize that to make predictions about it. But if it does not, then we will not be able to make a good prediction. Now if you look at this time series, okay, so now here you can see that there is a certain seasonality or certain cyclicity. So in the Monday's class, I was giving you some examples that time series has some typical components like a trend, like which is its long-term growth pattern. It has a cyclic component, that is to say a part of it seems to be going up and down at regular intervals, etc. So here is a time series whose cyclic component seems to be dominating. Not in this time series, there does not seem to be any cyclic component as such. That is, yes, it is going up, going down regularly, but largely that seems to be random. Yes, there does not seem to be any particular pattern between its rising and falling. Unlike this time series, where you can actually see that at regular intervals of time, that is from this peak to this peak, there seems to be a like a more or less constant time gap from this peak to this peak, or from this peak to this peak, from this peak to this peak. Again, there seems to be regular, like almost equal sized time gap, similarly between the different troughs also. Okay, so now if I make a plot of time series of this I mean a plot of correlations in this time series, so now I find that the autocorrelation is quite high, and for various various for certain values of lag. Say for lags of 250, we see a very high correlation. That means what? If you consider two time points which are separate from each other by a gap of about 250, like you can be sure that like they are behaving similarly. Say this point and this point, it may happen that the difference between them is roughly 250, or similarly this point and this point, again the time lag between them may be roughly about 250. That means what? That at length intervals of 250, that is, or if at any given time the time series is rising, then you can expect that 250 time steps later another rise will happen. If the current time series at any given time is falling, then we can again expect that 250 time steps later there will be a fall. Okay, so this property of correlation enables us to make something like a prediction. That is, if I know what happened to the time series values now, I will be able to say something about it, about what will happen to it after 250 steps. It will not be a complete understanding. I do not know the complete values, etc. But at least some idea will get whether it's going to rise or whether it's going to fall. Okay, so this is this autocorrelation. This basically sets the basis of time series forecasting through another concept which is known as auto regression. Okay. So sometime in your school level statistics, you may have studied about correlation and regression. right? There was like a linear regression whenever you may have studied in your school. You like along with the concept of regression, you would have learned the concept of correlation also. That is, these two are actually related in some sense. That is, whenever you find two variables which are strongly correlated with each other, you may use one as the independent variable and the other as the dependent variable, and you may use the independent variable to predict or forecast the dependent variable through a process of regression. Okay. So here also it's like the same thing. The variables which or the values of the time series which you have already observed are independent. Why? Because like you have already observed them, you will not be able to change them. But the future values which you have not yet seen, in a sense they are the dependent variables, because we know that the future is basically a function of the present and the past. Whatever has happened in the is currently happening, or whatever has happened in the immediate past, we know is going to have a bearing on the future. So we can say that the future variables, the future values of the variable is a dependent variable. It's dependent on what? On the present and the past. Okay? So based on that, we form a that forms the basis of what is known as the auto regression of time series, where we try to do is we are trying to predict xt, that is what the value of the time series at any point t, and and what forms the basis of that prediction? The past values of the time series. Say I suppose I have observed till t minus 1 and I am trying to predict what will be the value at t. So I may that is I may use the observation at t minus 1 to predict xt. I may also use the some of my past observations, say t minus 2, t minus 3, all the way up to t minus p prime, where p prime is any number which seems reasonable in my application. So I can use all those past numbers, to all those past values, to make a prediction of xt. Okay. Now, how do I combine those past values to make a prediction about the future? Well, I can build any function which takes all these past values as the input, but the simplest function is of course the linear function. The linear function means each of the past values I multiply by some coefficient and add them together to make the prediction. Now, the important thing to note here is that it is very unlikely that is, while it is very likely that the past values will have a strong impact on the future values, but at the same time it is also extremely unlikely that this will be the only impact. There can be other covariates also which are like influencing my time series. Okay, so now some of those covariates I may be able to enumerate by bringing in other by bringing in more terms in this auto regression, as we will just see, or we may just assume that there are some effect or various effects at every time point which I am not able to measure. Now those effects are arising from some other covariates or some other effects which I am unable to quantify. So those extra effects I simply consider as my error terms or my noise terms. Okay, so noise is a concept which you must have come across in various other studies related to engineering. So noise is basically whenever there is some process or which we are not able to measure or quantify or understand. In science we just pass it off as noise. That is, a noise is something like a random variable which just seems to be drawn independently at every time point from some distribution that has been given to us. Right? So white noise, etc. You will have heard of earlier. So basically, whenever I'm talking about some additive Gaussian noise or something like that, what I am trying to say is that in addition to the effects which I have already considered, in this case the effects being the past values of the variable, whenever those past values are not enough to make a perfect forecast, but I do not have any idea about what more are the factors that are driving on which the forecast should depend, I just assume that there are some noise terms like this. And in this particular model called the famous ARIMA model, or the autoregressive integrated moving average model, I consider not only the past values of the variable, but also the past errors or noises of the variable. So in a sense that this part is known as the autoregression, and this part is known as the moving average. Now so why is this called the autoregression? Because what I am doing here is basically nothing but a regression problem. So Professor Pulak Mishra might have shown you some examples of autoregressions by in some simple economic processes. So regression means what? Regression basically means I am using some variables to predict the values of another variable. When that is when the function I am applying on those independent variables, that whenever that's a linear function, it becomes a linear regression. And as you can see, yes, this is indeed a linear function. So here we are calling it as we can call this autoregression as the linear autoregression. And then these are the terms from the past. So this part we call as the moving average. Now, why exactly this is called the moving average, or what exactly a moving average is, etc., is beyond the scope of this lecture. I encourage you to read up about why this part is called the moving average. So we can write this ARIMA time series in various other ways, in a mathematical ways. So basically the thing is that this time series, this kind of representation, it has certain parameters, right? This p prime is a parameter and this q is another parameter. What is p prime saying? P prime is basically telling us how many past observations I should consider to predict the next observation. And what is q telling us? Q is telling us how many past error terms or noise terms I should consider to predict the future. But both the x, that is the past observations, as well as the epsilon, that is the past errors, are being used to predict the future. But the number of terms in the past and the number of observations in the past and number of error terms in the past may vary. Okay? So that is what basically the ARIMA model tells us. So now for different values of this p prime and q, you may see that the this model behaves in a very different way. So for example, if you consider this case, just a second. Yeah, so let us consider the case p prime is equal to 1 and q equal to 0. Then what happens to the ARIMA model? It is basically saying xt minus what? Let's go back here. P prime is equal to 1. That means we will have only this term. All the other terms will go away. So we are getting xt minus alpha 1 xt minus 1 equal to, what do we get on the right hand side? So although we had passed 6 minutes time, but because we lost some about 15 minutes or so, I will take about 5 minutes of your extra time. So if anyone needs to leave, they may please leave, because the recordings will anyway be available. The materials will also be available. So if now since q is equal to 0, that means what? That means I do not consider any of the past past noise terms. So I just consider only this epsilon t, that means the error term or the noise term at the current time. So this is what we get. Okay. So this is the way we are making the forecasting. Right. This is it's as simple as this. I am basically scaling the past value by a factor called alpha, or by a coefficient called alpha, adding some noise which I may be getting from some probability distribution, and based on that I am making a forecast of xt. As simple as that. Okay. Now what happens? Say if I put say p prime equal to 0, and q equal to 1. In that case, it will be like xt, nothing else on the left hand side. Xt is equal to epsilon t plus, look at the expression here, epsilon t is there, so q is equal to 1, so only this term will be there. So theta 1 times like epsilon t minus 1. It's theta 1 minus epsilon t minus 1. So in this case, the forecast is going to be just a combination of the previous error or noise and the current error or noise. So this is something which I may have observed earlier at t minus 1. Basically whatever was my forecast minus whatever was the actual observation, that was the noise at t minus 1. So similarly, this is going to be this epsilon t, I will get some random variable, I mean some probability distribution. So these two together will be my forecast xt. Okay. So similarly for other values, let's say p dash equal to 3, q equal to 0, let us say. So in this case, the our prediction model is going to be like this. Sorry about that. Never mind. Sorry. So basically this is known as the auto regression, which is used for time series forecasting. It basically it is based on the concept of linear regression, where we try to forecast the next values of a time series with the help of past values. Okay. So now where does machine learning come in here? So machine learning, as I said earlier also, machine learning is basically used to find the different parameters of the model. So so what are the different parameters of the model? So these alpha 1, alpha 2, alpha p prime, these theta 1s, these are all the parameters of the model. Besides this p prime q, these are also parameters of the model. So in the coming lecture, we will see how machine learning may be used to estimate the various parameters of the model. So the general idea is that first of all, you define a loss function to compare the true values with the predicted values, and then so like whatever forecast I am making, I will compare it with the actual observation once that becomes available, and then I will like measure their difference using a loss function. That loss function, what loss function I will choose is in my hands, but then I will choose the model parameters in such a way that the loss function is minimized. That is, I get as low a loss as possible. Now, addition in so that is the primary task of this this regression or this forecasting problem. Apart from that, also there may be some other things which I may want to achieve with the for regression. So for example, I may want some additional properties of the on the parameters. Say for example, sparsity. What is sparsity? Sparsity basically means like what do you mean by a sparse vector? Sparse vector means such a vector where most of the elements are 0. So now so suppose I have built a model like this which goes into the into many steps into the past to predict the future, but I actually do not want that. I want a like a sparse set of value regressors, right? So that is to say, I do not want to examine all 100 values in the past to predict the future. I just want to understand which values in the past are critical, and I want to use those only. So basically I want a sparse solution to this problem. So I want most of these alphas to, or as many of these alphas to become 0 as possible, as many of these thetas to become 0 as possible, and make the prediction only on the basis of the rest. Okay, so like how can we then choose the parameters so that these kinds of structural properties are satisfied? Okay, or if we suppose if I want to quantify the uncertainty, then again I may be in then what do I need to do, etc. and so, or suppose there are some other covariates or some other causal variables apart from the past variables and these noises also. Suppose I want to bring in some other covariates which influence these xt, then how do we take care of those? Right, so these are some of the questions. If we want to answer them, then we may need machine learning. Okay, so that's what we will study in tomorrow's class when we study about regression and regularized regression. It will give us a family of models which will or a family of methods which will which can solve which can be used to solve various problems related to time series forecasting in economics. They need not be related to time series forecasting also. There are also some non-time series problems of in economics where these concepts of regression and regularized regression become handy. So we will discuss all of them in the next class. Okay, so so sorry for the delay and the subsequent extension of the time. So so we will again meet tomorrow and we will continue this discussion on regression. Okay? Thank you.
Thank you, sir.
Thank you, sir.
Thank you, everyone.
Thank you.